Again, in case you don't know who I am, my name is Billy Lamberti, and today I'll be talking about inferential shape proportions and encircled image histograms, or in the vernacular, iSPEI. So a little bit about myself. I have my master's in statistics from GMU. I'm one of the presidential scholars in the CDS department. Outside of academia, I've interned at NASA. I founded rgallium.com, which is this introductory R and statistics website for individuals who have no prior programming experience or statistics experience to start learning some of the basics. And outside of that, I've led into some consulting where I've done introductory R and statistics lectures at places like the National Opinion Research Center and NASA. And then some of my research interests involve image analysis, or what is sometimes called computer vision, shape analysis in specific, and then using lots of statistical and machine learning algorithms. A lot of what I'm showing today will be preliminary in nature, so if you have constructive criticisms, helpful suggestions, please feel free to jump in and fire away, and I'd be happy to consider them. So what I'll be talking about today is the problem of pill classification, some overview of what the goal is and what the eventual desired outcome from that community will be. I'll be talking a little bit about the NIH pill database and some of the unique characteristics of that data. And then I'll be talking about the contributions that I plan to outline in this talk. I'll do a review of what SPEIs are, or what shape proportions and encircled image histograms are, and then I will get into the meat of the contributions, which is the iSPEIs, the inferential shape proportions and encircled image histograms, and then I'll end on some future work and directions that I can take this. I hope to take this. So an overview is, it's very desirable to be able to just take a picture of a pill and automatically identify it. So if you had an Advil right there, you just want to take a picture with your smartphone and then have the app automatically identify, oh, this is Advil. This would be desirable by law enforcement agencies to investigate what drugs a person was taking or when they overdosed, perhaps. It would be desirable by consumers, so maybe you dropped a bunch of pills and they all look very similar and you just wanted to put them right back in the right categories so you didn't have to pay more for these pills. And then another example is in the health industry. So there was an exploratory study in Norway where what they tested was, do the patients actually receive the medical pills that they're supposed to be? So the doctor prescribes a pill that they're supposed to get in the hospital, and then they check to make sure that they actually got it at some other time point. Turns out over half did not. And so, again, this is exploratory, and this was only done in Norway, but this shows that there is a desire, at a minimum at this hospital, to have some kind of system that is able to identify the pill and make sure that it corresponds to what you're taking. So what would happen is you would have the doctor write out the pill, and the technician or the nurse who's filling out the prescription would then fill it out and then put those pills underneath a camera, take a picture, and make sure that it actually matches what is in the computer system. And then the patient would receive the correct dosage. The correct dosage or correct pills. And so at a minimum, there is a need in various parts of society to have a pill identification system in various different levels.
Well, just on the Norway data, what strikes me as being, it's a very high rate, very high number, so, which presumably would be lethal in many cases. So is it, was it partial, or is it just kind of like they're giving the wrong dosage?
So some of it was wrong dosage.
Yeah.
And so, again, this was exploratory, so in this case they did 30 patients.
Yeah.
So it wasn't like they did it for a large sample size. But the point was, is this worth even investigating? And it seems like the case is that it is. And so that's the most recent data that I can have to show that kind of a specific example. But this is just it's just trying to provide more evidence saying that you can have a pill identification system that would have a meaningful impact. And while those cases may not have been fatal, it could very well have been if you accidentally mix too much of a dosage with other pills, or and so on and so forth. So in the end, the goal of this problem is to correctly categorize pills, but because that is too difficult of a problem, we're not able to correctly take a picture using a smartphone of Advil and correctly identify that it's Advil. The pill research community has said, okay, I'm going to focus on getting pill color right. I'm going to focus on getting pill text right. And I'm going to focus on pill shape right. The goal for what I'm trying to do is to correctly categorize pill shape classes.
Well, so you want to fix, there's a problem to be fixed, and you're going to, by being able to do the classification, will help fix the problem. Just out of curiosity, do we know anything, have there been any models built that you're aware of for this business about kind of like, how pills, in essence, end up in the wrong hands, or, for example, so between the process of having the doctor write out the script, having it go to the pharmacist, and the pharmacist, actually creating the right dispensary, whatever it is. I mean, presumably the pharmacists in pharmacy school get tested on this, and they're not going to pass unless they can do a good job at that. Right. So there's these kind of separate processes. Then once it gets dispensed by the pharmacist, then it either goes through the nurse or not. It goes to the patient, this or no, whatever. So are there any models of that process? I mean, that's strictly speaking, it's a chain process where any set of errors could accumulate. I understand that. Right. It'd be nice to have that running in the background a little bit. Right.
So just to further clarify, the healthcare industry example that I said was specifically the doctor was at the hospital, the patient was in the hospital, and they didn't go to a pharmacist per se.
Well, but the hospital probably has its own pharmacist.
Yeah, that's true. I'm just making sure it's not like we're not going to CVS.
But I'm just saying, there's a non-trivial process involved, and I'm just curious as to where the weak link in that is.
Right. So from my understanding, there is, or rather, I have not looked into that model. I do know from speaking with other pharmacists is that the reason they take so long behind the counter is that they're carefully measuring what the doctor gave and making sure that you don't have any other interactions. Exactly. So I do know that there is a lot of effort put behind the counter at like CVS or Walgreens or wherever you get your pharmacy drugs, but I'm not familiar with the specific case of like at a hospital.
I just wonder whether these are the cases in like the operations research that people have built models of this or something.
Yeah, and I'm not familiar with that. That might be because this healthcare industry study was relatively new, and so maybe now people are like, oh, we need to investigate what this process is and make sure that there aren't missing holes.
Well, I wonder if we called up Kaiser or something and said, yes, because they do everything in house, right?
Right.
They're going to be able to know. We have like 1% mistake rate on these things. And we've identified that usually it's either the doctor or the pharmacist or the nurse or whatever. I wonder if those things existed.
Yeah, and so
or whether they'd be willing to share it.
Fair enough.
Yeah. No, so those are very good questions, and I don't know, but that's definitely something I hope to find more about. Great, and so to make sure it's explicitly clear, I will only be looking at 2D digital images. So I won't be looking at 3D images, 3D brain scans. It's just 2D digital images is the kind of problem I'm focusing in on at this time.
And I remember you talked about this last time. They will be color, right?
So I will go over a little bit right here about like what's going on. So image operators are used in a lot of different scenarios, and this is just an example of how you can use image operators to get information about the pill data. So here is an example of just a capsule pill. This is your original data, and then using some edge detection methods, you can find the edges of that pill. So you can see here that we found the edges for the text on the pill. We found the two different capsules here, right? And then from plot figure 2, we can just say fill in the edges, and now we have the pill shape. And so while I'm interested in subplot 3 here, this pill shape, you don't have to just use this for shape analysis. You can use it for lots of other things. So for example, if you combine plot 3 and plot 1, you can get rid of the background and just extract the pill. And you might want to do that to isolate the pill and do a color analysis model, or to isolate the pill from the background and do a text model. And so you can do lots of different, the point is you can do lots of different things using image operators, but I am interested in only this figure right here. So I'm going from the original image, finding the edges, filling in the edges to get the shape. And I'm interested in these shapes. That's what I'll be analyzing.
Can you always guarantee you're going to be looking kind of orthogonally at it? I mean, obviously this has lots of degrees of symmetry, but what if you had some oblique angle?
Mm-hmm. Yes, so I have seen people try to do, like, orient the pills, but the point of the approach I'm presenting is that I don't care if it's at an angle or not. And so that it's invariant to orientation, which is one of the things that you desire for shape metric.
Is it the case that you don't care about? No, it's in 3 dimensions, so you don't care about any angle at all, or
right.
how about the and as the azimuthal angle, like, you know?
Oh, I see.
At it from the,
I see. So if you're
right?
saying if I just got a picture from like the top and only got the blue part, yes, then that would be, I would care about that. But if like the lily was upside down,
yeah, then
I wouldn't care. Or if this blue part was pointing in this direction and the white part was pointing in that direction, I don't care about that. But yes, I do care about getting the front correctly. That I do care about. At least for the approach that I'm discussing today.
There's been a reasonable amount of work in robotics on identifying randomly placed objects to be able to pick and place.
Right.
And they're in all sorts of orientations in 3 dimensions.
Right.
Any of that useful?
I have not looked into that, but I imagine that you would have problems, especially with capsules. So like if you orient this so that you're looking at the top of the blue and just saw basically a circle, you're going to have, that looks like a circle. So it's a candidate capsule or a candidate round pill. And so you still are going to have that issue there, because unless you know that unless you like look at the other side and see that what the 3D shape is, you're stuck with only knowing that it's round. And so you would need more information to deduce that, oh, I have another side to this. What I'm talking about today is just the problem of this is my original shape. I have no other sides, no other slices. I just know that this is the case. However, if you had more of a 3D view, you could definitely say, oh, well, on one side it's a circle, on another side it's a capsule, and then again on another side it's another circle. So that's probably a capsule or an oval pill. So there's definitely ways that you can expand this. I'm not focusing on those problems today. I'm focusing on the problem of you have the front or the back correct, and that's what I'm going to use to analyze the pill. And so the data set that I hope to eventually be applying this to, what I'll be talking about, is the NIH official pill database. As of June 2018, it had over 5,000 pills with a total of 15 different classes. And here's an example of what it looks like in the NIH pill database. So you have this it's not consistent, but one of the examples is that you have the front and the back, and then you have some kind of unit measure reference point. And one of the unique aspects of this problem is that the data has vastly different counts for the classes. So for the semicircle, which is basically just a semicircle, you only have 2 of them, while the circle has over 2,000 examples. And so the traditional machine learning, deep learning approaches where you have lots of different cases to train your model, you don't have that in this scenario. And so the challenge is, can we develop a method that can handle this scenario of data?
Is the database consist of images, or does it consist of some analytic geometry about the images?
It consists of images.
Okay.
They have some that don't have images, and those I'm not looking at. But it's the image.
And are they of homogeneous quality? But if they're the same resolution pixel-wise, no.
So some of them are okay. So when they initially did this, they were all the same quality, and then they added to it a couple years later, and then they have a different quality. And then they added more later on at a different quality. So it's not consistent whatsoever.
Is it basically a JPEG file, or is it something more like, is it raster vector? How does that work?
I forget exactly how they save these. I think these are as TIFFs.
Okay.
High resolution TIFFs, or
pardon?
High resolution TIFFs, or
some of them are high resolution,
okay,
some of them are lower. I saved them as I did a lot of my analysis in JPEG, but I have not investigated the specific differences of analyzing the JPEG versus PNG file conversions. I would imagine that it's not a severe problem in this case because a lot of the PIL images are high enough resolution for analysis. But we will discuss some problems if you do have low resolution images and how to and what those challenges might be. And so the contributions that I hope to explain today is to expand SPEIs to the cases where they deviate from known shapes. So in the past I discussed how SPEIs can be described for certain kinds of shapes and how they exist in reality. However, what if you have, and so one of those examples, well, they were for regular polygons and circles. Like, we're able to define how those shapes exist in reality. The problem is, what if you have a slightly non-regular triangle? Or what if you have a rectangle? How does SPEIs work when you relax the assumptions of regular polygons? And I hope to provide a framework to apply inferential SPEIs to non-2D digital image data. So I hope to provide some kind of framework from now relaxing the assumption of regular polygons and circles to then apply this to data that does not have a polygonal shape. So maybe a spiral galaxy. Can I classify spiral galaxies from edge galaxies? Can I classify human action videos, which are not polygonal? Someone doing a jumping jack does not look like any polygonal shape, or what a traditional polygonal shape. And so my second contribution is to provide some kind of framework that I can then try to apply to other image classification problems. So let's review what SPEIs is to make sure everyone's caught up to speed. SPEIs, or the shape proportion, describes shape as a proportion. And I then can utilize the binomial distribution to make inferences on how that shape exists in reality. And that realization of that shape, going from abstraction to the discrete digital 2D space, or from the continuous space to the discrete space, I can use encircled image histograms as that realization to then try and do classification. So in very broadly speaking, what happens is that SPEIs starts with a circle, and then you put that circle in a square, like so. And then for a given shape, so what happens for a given shape is you put that given shape in a circle, and then you put that circle in a square. that provides a unique reference point that provides a unique value for regular polygons and circles. And so here's an example of what the result would be for after applying SPEIs. You would have without the reference circle. So here's a square. And so to really understand why this setup is valuable, is because if this is all the information you have, I don't care where the pentagon is in the square, right? If this top point is over here, the white area is still going to be the same, composing the same amount of total for the total image. So in other words, the white here, the white proportion of white pixels will be the same no matter what orientation this pentagon is on the circle, because the amount of black area will remain constant. So if you just imagine swirling this pentagon around, no matter what, it's always going to the pentagon is always going to reside on this circle, and the square won't change at all. So again, with a square here, if this point was over here, it would still be like this box would not change. So there are approaches that just use a bounding box. A bounding box is very different from what I'm describing. A bounding box just says, give me the minimized encompassing rectangle for that given shape. It's very different from what I'm describing. Bounding box would provide different proportions for a square, for example. For this case, if you just did a bounding box, your proportion of white, your number of white pixels divided by the total number of pixels composing of that image would be a half. If this square rotated by 45 degrees so that this bottom part resided on this bottom part of your bounding box, the bounding box would be the image. And so therefore the number of white pixels over the total number of pixels in the image would be 1. And so you're providing different values for a given shape. And so not going into the proofs of it all, here are some examples of some SP values for different shapes. So for a regular polygon with 3 sides is about 0.32, and then you can go up to 10 sides, which is about 0.7347. Basically what you have here for regular polygons and circles is that you have eventually the regular polygons converge to a circle, and so eventually the regular polygons will converge to pi over 4, which is the SP value for a circle. And so here's another example to describe what's going on with a SPEI. And so here's your original image, and here's an original image of a polygon, and over here is the black pixel counts and the white pixel counts. Excuse me. After applying SPEI, what happens is basically you have the black pixel counts went way down, but the white pixel counts remain constant. And so here you can visually imagine that there's a circle encompassing this polygon, and that's going to provide very different metrics than this one. And so here's a comparison, just again to really drive home this point, is that the encircled image histograms changes the number of black pixels while it leaves the white pixels consistent. So that's the intuition behind what's happening with SPEIs, is that you're changing the black pixels and making it appropriate for the given shape. And this is based on the binomial distribution where you have x is the number of white pixels or the number of successes. You have your sample size, or the number of trials, or your sample size zeta, which is the resolution or total number of pixels in the image. And then our proportion, or probability of success, is our SP value. And so here's an example. I provided this last time I gave a talk, where we have regular polygons with a side length from 1 to 125. So here's 4 different examples. Here are 2 examples of side 1, and here's examples of side 125. And so now let's apply SPEIs and see what it looks like. And so from here, after applying encircled or SPEIs to the data, you can see that each of the classes follow these lines. And on here are the 99% credible intervals for the data, and they're pretty close to the observed EI values are pretty close to the theoretical confidence or credible intervals. And so this seems to suggest that SPEIs is theoretically sound, and that this seems like an appropriate approach or appropriate method of classifying different shapes.
It's not obviously the most intuitive one, though. So are there other things that are used in practice, or other things out there that are?
So other shape metrics.
Yeah.
So there's one of the examples that one of the most comparable examples is a measure called circularity, which describes how circular a shape is. It also has the unique contribution of having unique values for regular polygons. There's a problem with it, though. The values for circularity for regular polygons have no interpretable meaning. So how do I one of the values is 0. What does the circularity value of 0 mean in reality? An SP value of 0.5, that means, oh, I should expect half the pixels to be white and half the pixels to be black. And then given a resolution size, I can say I expect it to be this value. And then maybe there'll be some deviation from that. Circularity doesn't provide that. Another issue is when you actually apply this, you get values that deviate from your theoretical value, right? So instead of it just happens in data. You have noisy data, you have edges that aren't perfectly straight, etc. And so what happens when you observe a value of 1? Is that close to 0, or is that really far away? Circularity provides no guidance on that. So yes, there are other metrics out there, but I believe that this is the first one that provides a theoretical foundation so that I don't even necessarily need data if I know the SP value. If I have the SP value, I know what I should expect.
Just out of curiosity, what is used in other parts of the stats optimization world where you need to do this kind of thing? Because like when radar people typically have 2D images, and they have to identify whether it's our tank or their tank. I think that they're just using some kind of giant lookup table, right? Those are irregular polygons, obviously.
Right. So what they might do, like another example would be doing satellite imagery for planes. Right. And so you basically have lots of training data and saying this is what we trained our model to look up these types of planes, and then you train the model until it performs well, and then you apply it to real world data, and that's how you
the black box.
Yeah, so there's that approach as well, where it's very irregular scenarios. The circularity metric was something I described that's much more has a lot more. It was developed in the 70s, while a lot of the training model things that I was just discussing is more recent advancement, relatively speaking.
Yours is more mathematically interesting. I'm just curious as to whether would we expect them to outperform a highly trained black box?
So I have not seen that for pill data. that is something someone suggested to me as a great addition to my proposal, and I'm hoping to incorporate that and see what the comparison is for comparing pill data where you have very few training sets to something where I can exploit some underlying relationship between the abstraction of a shape to the discretization.
There's also, in this case, you have very few training sets, but just out of curiosity, wouldn't it be also the case that you could imagine ways you could get a lot more training data, right? You could just take some of those pills, right, and just start photographing them at all hours of the night, day, whatever, and odd angles, etc., and you could build up a gigantic database that way.
No, that's true. And so you could go through that process. And so there's a. This week someone pointed me to something called Training with Less Data. It was a presentation by DARPA, and they were trying to investigate how can you do machine learning AI with less training data, and they were explaining how costly it is to get the training for these large databases. And so this exploits that by not needing as much training data.
It seems like the question on the table, the black box versus this, though, seems to be the advantage of this whole setup is so long as you've got a symmetric error term, which is orthogonal to your predictors, then it sounds like this would do okay because you're not going to change that polynomial fit by just randomly flipping pixels white to black so long as you're doing so symmetrically. But if that error term is not orthogonal to your data, which in real life it never is, the question is how bad.
Or how fast do you degrade? Basically.
Yeah, then you might get better performance with the black box. Like I'm just thinking, some pills are shiny and some pills aren't. Shiny things produce glare when photographed with a flash. That could mess with things, but maybe it's not a big deal, especially given that this is so far monochrome.
So one of the solutions to that is in the image processing. There are different color spectrums that get rid of sheen and gloss.
Okay.
And so you can exploit, basically knowing how your data is captured is really important during this step. And you can use appropriate color models that ignore gloss and sheen in those scenarios, which is an important point to make because you have oval pills, right? Maybe like fish oil pills. Those are naturally glossy. And so absolutely making sure that you account for glossy images or those kinds of obstructions is really important while trying to just isolate the pill shape initially, or any kind of shape in general.
Can you go back one slide to one more? So on this thing, so I mean, I understand this is a good way to, in essence, count the pixels. But it strikes me that it's a fairly crude thing in the sense that in reality, right, there's a whole bunch of spatial correlation among those pixels, and this is not counting that at all.
Right. So
wouldn't you want something like a Markov random field or something like that to do a much more thorough job on it? Right?
There is. I'm currently investigating. One of the things, the future parts, is to investigate how badly this assumption is violated and to see what would work best.
Well, the issue is it's not going to be violated anywhere except where it matters, like on the boundary, right?
Well, okay, so imagine a binomial random variable. A very simple example is flipping a coin, right?
Yeah.
If you had a fair coin and you flipped a coin 5 times, it's unlikely, but not completely out of the ordinary, to observe 0 heads, right?
1 out of 32 times.
What I'm doing is allowing for, I'm saying I cannot allow for complete failure or complete success. Why? Because I'm saying take the shape and put it in a circle. And then put a square around it. It is impossible for any shape to get around here. I cannot have 100% success, even though the binomial distribution allows for that. So yes, this is a crude approximation, and I'm investigating how badly that approximation does, and how I can appropriately define what the exact setup is. And my preliminary investigation suggests that it's some kind of mixture model of some kind of discrete 3 different discrete distributions. I literally can't say more than that because I don't know more than that because the simulation's finished today. So I will hopefully have more updates on that. But as a crude approximation, the binomial distribution at least seems to be doing somewhat well.
We can come back to the end, but I guess the point that seems to me to be missing from it is just that a mixture of distributions, you're still counting pixels on and off, and you're just trying to figure out where the boundary can never be on, etc. But in reality, it's a spatial problem, right? The fact that one pixel is on means there's a higher probability that a neighbor pixel is on.
Right. No, so that's another aspect, and I was just trying to add on saying I'm also not allowing for 100% success. You're absolutely right that the lack of having IID observations is also an issue, and that is something I'm trying to investigate. Absolutely.
Have you considered it in a information theoretic sense about, because I have the feeling that your binomial distribution is assuming any neighboring pixel has the same probability of being on or off, which is an awfully strong assumption when there is some spatial representation to it, where an information theoretic approach might try to carry some of that.
So are you just saying use entropy, or using something more sophisticated than like?
Start with entropy.
Start with entropy and move from there. I have not, but that's a great consideration.
Didn't it? Technically, there's a whole area called excess binomial variance. So you're going to basically say, right, I can figure out what fraction of pixels are on, what fraction are off. And now and the point is that the ones that are on are all clustered. Right? Yeah. And so this excess binomial variance has been used by various communities, including like criminologists, even to say, like, if I look at the where the crime happens in a city, I don't see it's uniformly.
Right.
Even though the chance of having a burglary tonight is, say, 1%. It's not the case that there's 1% across the whole city.
Right.
It's clustered, and then they compute excess binomial variance to figure out where where the spatial statistics are important to include and where not.
Okay. So excess binomial variance is what.
And so I think it's an area within spatial stat, and of course spatial stat is the kind of thing that none of us really do well. Right? We talked about we should know more spatial stat, and it's all the kriging and all that kind of crap, right? It's not easy going, but it's Markov random fields and it's Gibbs samplers and it's all that stuff that.
This is a noxious tendency to violate assumptions.
Yeah. Right.
That's the problem. Yeah.
Okay. Those are great suggestions. Thank you. Okay. So now we're actually finally getting to iSPEIs. So what if we have a class that doesn't have a known SP value? Here's 2 very basic approaches. One, just calculate the observed encircled image histogram values for each observations and build a model just based on that. Don't make any assumptions about the distribution, just do that. Another approach is to estimate the SP values from the data and then predict the EIs using some statistical distribution from the estimated SP value. And you can theoretically come up with other approaches, but these are just 2 approaches that I'll be discussing today. And so just using the created data, if I just make a quadratic discriminant analysis model, if I consider all the images, I can get a misclassification rate of about 0.14. But if I consider only the larger ones, or the ones with a total resolution size greater than 100 squared, because I'm using each side of the image is going to be the same, so it's 100 squared. If I use those, it's less than 2% misclassification rate. Now let's try and do this. If I assume a binomial distribution and I use a hierarchical model where each resolution is its own setup, basically, of a beta binomial conjugate pair. If I use that setup, I will get a misclassification rate of about this exact same using all the data. But then if I just use the larger ones, I'm able to get about 2%. And so very comparable to quadratic discriminant analysis approach of just using the raw output and not estimating the SP values or anything. And so on this plot over here is just the posterior means for all of my observations. The posterior credible intervals, 99%. The theoretical value in the red line for the triangle. And this black line is just a reference point. And so we can see that most of the credible intervals seem to be containing the red line. And so that means that they're able to capture the true SP value. And so again, this approach, at least practically speaking, seems reasonable to make this assumption of the binomial distribution, even though it's probably not correct. Let's complicate things now. This whole time have been working with created shapes. Those act very nicely. Let's work on a very small image data set, for an image pill data set. This is a subset of the original data set that I showed previously. Here, we're just looking at triangles, quadrilaterals, pentagons, hexagons, and circles. We still have very similar scenarios where we have lots of certain classes and very few of other classes. And to give an idea, here's a circle or a round pill. Looks exactly how you would imagine. However, you have lots of cases in your pill, in these pill images, that do not look like what you might imagine. So this is a triangle pill. It looks more like a shuriken. And so you have this noise, if you will, to the shape. You have these deviations from what you might consider a regular triangle. And so now the challenge is, or the question is, do these greatly deviate from the theoretical values for triangle, square, hexagon, etc.? And then also, can we estimate what those SP values if they deviate? Or can we just create a model that works well without even knowing the SP value? And so here's just, when we apply SPEIs and calculate the data, here's the output. The points indicate the observed value, and then the dotted lines indicate the credible intervals, assuming that it's regular triangles, regular square, etc. And so for circles, you can see that it's a little off, but it's fairly close. However, for a triangle, you have these great deviations from what a regular triangle would be. And so here, there is definitely a need to be able to estimate what these SP values would be. Well, let's do approach one. Let's just say, I just want to calculate just give me a model that uses these and is able to estimate or try and classify the observations. And so if I just look at a naive model of just classifying all the observations, I'm able to get less than 1, or about 1% misclassification. However, because we have so many circles, that may be a misleading statistic. And so when you remove the circles from the classification rate, that is about 18% misclassification. So you're misclassifying some of these other classes using this approach.
Can you just clarify too, Billy?
Yes.
And when it comes to classifying pills, shape versus what the medicine is, I mean, so here the error rate basically is this is the error rate on your shape.
Yes.
Right? But if in fact there's 2,000 pills, we still don't 2,000 round pills. We have no idea what the medicine is inside the pill.
Correct. So the round, so for example, if we were able to create a pill, just a model that distinguishes round from other, you could say, okay, great, this is a round pill. But now there's still the needed step of saying, okay, well, what color is it? What's the text on it? I still need to know what it is. And so yes, this is not saying, oh, this is going to, if you give me a round pill, I will be able to identify what kind of pill that is. This is just saying classifying the pill shape. And so this is again just an approach at using SPEIs. I have not added any other variables or done any other metric collection. So you can imagine that if I were able to obtain other useful metrics, this might even improve even further. The point of this is just to say, how well can SPEIs do, or inferential SPEIs do, in this for this problem? And so now if we do the same approach as we did before, we do a hierarchical model, we learn what the SP values are, we use the beta binomial conjugate pair. With that, we can get 2% misclassification error using all. But if we remove the circles, we almost double the misclassification rate. And so there is, this kind of provides some evidence that maybe the beta binomial is not the appropriate setup for the SPEIs, and maybe another approach is better. But this is an example. Remember from before, though, this is the hierarchical model for the posterior's means and credible intervals for the triangle class, for the created shapes. If we look at the means and credible intervals for the posterior for the triangle class in this observed data, you don't even see the red line. It's not even in the conversation here. And further, you have potentially 3 different means, different shapes.
Yeah.
And so this implies, at a minimum, that these pill shapes are not going to be consistent for every single class. So there's going to be subclasses within classes, if you will. Okay. So in the future, there is a lot of work to be done on appropriately estimating the SP values. And one of those things is investigating if the binomial distribution as a starting point is even appropriate. Another is to develop a method that, once those SP values are estimated appropriately, can that be exploited for classification purposes? Using a modeling method that is explicitly using those SP values in a direct approach. Because the hierarchical model is estimating lots of different SP values for each different resolution. What I'm desiring is one that can use those different resolution sizes or the SP values across different resolution sizes and use that estimation appropriately or effectively and efficiently. Another area to investigate is applying a bootstrapping-like method to get more observations for different classes. So if I only have 2 observations for the semicircle class, I want to be able to sample those 2 observations repeatedly to kind of get more data. And it's that method would be partially inspired by the bootstrapping method from statistics that you might have heard of. And then another area is to apply iSPEIs to other 2D digital image data, such as galaxy classification. Are there any questions?
You've asked a lot already, I guess. Imagine that you had this done. Imagine that you had all the shapes classified. Would you want to then go into them trying to do pill identification? Is there a next step to do that?
So you're asking if let's say I got 100% classification rate,
right.
then the next step is to
Advil versus Tylenol.
Advil versus Tylenol. That's a possibility. I think the next step would be to see if this approach is applicable to non-polygonal shapes at all. I want to see if this can be applied to that. And then I would also want to see, can I then extend this to 3D images? So does if you have two different brain segments, 3D segments for two different patients, one that has cancer in that segment of the brain and one that does not, do these shapes differ? And basically in that scenario, what you would be doing would be, instead of doing a square, you would be putting it in a cube, but putting a shape in a sphere and then a cube, and seeing, can we distinguish 3D shapes using this three-dimensional SPEI where you're putting things in spheres and then cubes. So I'm interested also in trying to extend this from 2D to 3D.
It seemed to me that if your crude binomial assumption turns out to actually be really important, it would be in that extension to more general shapes. Because, it's not a polygonal assumption that bothers me. I can see how if you don't assume the shape is convex, that's going to make this much, much, much harder. And that's where your sort of crude sampling measure might, might actually be the best thing we can feasibly do.
Yeah.
Well, yeah, a galaxy is almost like a fractal object, right? It's like a limit by the resolution. You only see certain of the stars, and it seems like a very different problem.
They have a different structure. They're not solid, like these pills are.
So a big part of that is the image processing. So first you collect the edges, and then you fill in the edges. That process of collecting the edges and then filling in the edges is a question of how much, it's a tuning parameter, if you will. You have to adjust the tuning parameter to capture the shape that you want. And if you were not looking at it at a fractal point of view, you're looking at it in basically the digital space, the 2D digital space, you're saying it's a tuning parameter that I have to adjust to make sure I capture the shape across all classes appropriately. And the best method that I'm aware of at this point is the Otutsu method, which basically assumes that you have two different colors in your image, and then basically it categorizes them as either belonging to one class or another. And that works well for galaxies because you usually have a black background, very dark background, and then everything else has color, which is added, but it has more of a brightness to it. And so that is what is used a lot in galaxies, is the Otutsu method.
Yeah, stupid question about pills. They're a manufactured shape.
Yes.
I can imagine there being cost benefits to making them basically round, but I can also therefore imagine that there's some cost to making that funny shuriken looking pill.
Yeah.
That people are paying for.
Right.
Is there something else going on in the pills? I mean, could we regulate that they all have to be round?
So I wouldn't want that because then there's no Flintstone vitamins. But so I don't know why. I'm one of the possible explanations that was offered by Dr. Eagle is that you can trademark a pill shape as being unique, right? And that might be one of the benefits, is like, we have a unique pill because it's this different color and this different shape, but not necessarily providing any other meaningful difference between another Advil.
Like the Flintstone versus Scooby-Doo.
Yeah.
I mean, when we know that Advil exists, so apparently people do value that.
A perfectly round, I mean, a traditional round pill.
I just mean branded ibuprofen versus generic.
Yeah.
Because, I mean, if you go to the CVS, there's different grades of ibuprofen pill. But there's branding on top of that. You can get a CVS brand that's identical in every way, more or less, to the Advil, but it's cheaper.
I take a pill, and I've noticed that I have they come in two different shapes, and my doctor originally prescribed the trademark, what is the brand name version rather than the generic, and he said that a reason for doing that was that the accuracy of the active ingredient was significantly different between the generic versus the trade name one. And in that, my understanding is they only use the color to differentiate the doses. So I think there's lots of interesting stuff going on with pills that I don't have much knowledge of.
And obviously there's a difference between prescription pills and non-prescription pills, and so that is another consideration that there's more to learn in that area.
Yeah.
The latter is presumably less urgent because it is possible to overdose on non-prescription pills. Obviously,
but it's
like
difficult.
obviously, ibuprofen has a lethal dose, but I don't think that's usually what happens, right?
So it happens when you have kids and they eat all the Flintstone gummy vitamins.
That's right.
That'll happen. And granted, maybe that's not happening to most of the adult population, but it might happen to some.
That's an argument for making vitamins nasty.
Yeah.
But then they won't take their
Which was the whole point in the.
You missed the
Really,
point.
there's got to be a sweet spot where they're not tasty, but they're not, vile either.
Right.
So, is there an advantage to splitting up this problem into shapes and text and colors versus just doing sort of a black box model on the whole thing?
It
Shapes,
just doesn't work.
It doesn't work.
Like so you can get like really high classification rates, but you don't get 100. Mm-hmm. And are you willing? And so the question is, if you implement this and then put it in a pillbox monitor for an elderly person who's maybe getting early stages of Alzheimer's, that needs to be monitored, but maybe is not at the point where they have to be monitored every day. I mean, they could just forget to take their pills.
Right. But so your point is that you need 100% accuracy because the consequence of being wrong is high.
Exactly.
I'm not going to go.
Well, I guess I'm less persuaded of it now than when you started, just because you're only getting the shape, right? You're not. So imagine if an older person has 6 pills they're taking, and if the proportions are similar, maybe 4 out of the 6 are round.
Yeah.
Well, that you'll combine this.
Yeah. So I'm not saying, you should just use my model to do everything. No, I'm saying that yes, like the community and then once we develop a color model and a shape model and a text model, and we're able to, create that model that combines all 3 of these aspects, then that kind of implementation would be appropriate. And I'm not saying that I wouldn't be interested in that, doing that eventually. But I'm also interested in developing the shape model for 3D shapes and also non-polygonal shapes.
I'm curious too about this. I mean, it seems like many of the deep learning algorithms have, in fact, we find in the social sciences they're not oftentimes really useful for our social science data because they've really been they kind of cut their teeth on doing things like image analysis and that kind of thing, right? I would be curious to know what the background. If you're like, I know you have only a few training cases, but it seems like you can always bootstrap a bunch of other training cases by just rotating the thing a little bit or something, right?
No, that's exactly what I was thinking.
And then if you did all that, could you train a deep learner? And I'd just be interested to know whether does it have a 14% error rate, or is it 99% error rate, or is it like 0.00014% error rate?
Right.
It's nice to know what the.
You basically described exactly what I was thinking of for the third step. It's developing this bootstrapping method where I'm basically rotating, shifting, etc. And that is how you get more samples.
Add noise or just.
But you basically described exactly what I was describing.
I'm pretty sure, but I have a brother who works in the Department of Defense, and I'm pretty sure those radar guys have gotten incredibly sophisticated about looking at 2D images and turning them into targets will fire, not even putting them on like automated algorithms and stuff, right? So they have very high confidence. They have like 99.99% confidence. That is a Russian tank.
Right.
Mm-hmm.
So that's Black Sky, which has been doing some training sessions in the College of Science, has been basically describing a lot of those things. And so it's deep learning though. Exactly. And so the problem is, what about those cases where you don't have lots of training sets, and can you bootstrap in some method.
But in your case of the pills, see, it's such a the beautiful thing about the pills that it's such a constrained space, right? I mean, I don't imagine that you say you put out a request for proposals for people to provide more images than those 5,000 or whatever. Right? I mean, but I think a perfectly valid set of new images would just be taking your existing ones and just, as you said, rotating them or spinning them or doing something like that. Those are good. Those are perfectly valid new images, right?
Yeah. No. So that's exactly.
So in some sense, you actually have a continuum. You have an infinite number of images right now, right? Because you can just rotate them a little bit, and it's
right. And so the question then there, because so what's happening is that you have a starting image, and you have a rotation matrix, right?
Yeah.
And so you can actually deterministically figure out what all those values are. And so the question is also something worth investigating once that kind of bootstrapping method is developed. How big of an effect? Like, is it practically random or not?
Yeah, right.
Like that's actually a consideration. It's like how practically random is your bootstrap data? That's something I'm interested in, because you can actually calculate given rotation and your algorithm for, because like if you have a pixel, like if you rotate this by a little bit, like would this pixel still be white, or this pixel now be white? Right. So that algorithm that determines that, is that practically random? All those things are worth considering when developing that kind of bootstrapping approach.
And I'm imagining someday a robot runs around the hospital with your algorithms inside it, picking up off the floor all the pills, because the pills are free in the future and just laying all over the floor.
Yeah.
And then it has to classify them and put them back in the appropriate place, right? And,
that's under the assumption we're still using pills, and it's
right
not just it's just a spray.
Right.
But they're talking about doing food by pill, like from Willy Wonka, and so great. There's no medical pills, but there's food pills. Don't want too much vegetables with my hamburger pill.
I don't really see food pills taking off.
Yeah, no, there's too many exploding
not food
blueberries.
pills, but pills by food.
Yeah.
Brand.
Presumably the robots are going to look like the ones wandering around campus.
So we're all going to be on a starship?
I don't know.
Any other questions for Bill?
No.
Thanks a lot.
Yeah.